Hi everyone. In today's session we'll see the speed control of induction motor by AC voltage controller. The applications like fan, industrial fan, pump type or even home appliance fan where we'll use the single phase induction motors. So all these are controlled by using this AC voltage controller. So if you see the single phase AC voltage controller circuit diagram, we'll use the triac switch. Triac is nothing but back to back thyristors. So it is a single switch having gate pulse here, and the single phase AC supply is connected here. The output is connected. Output of this triac is connected to the induction motor. The output current is I naught and output voltage is V naught. So this is for low power applications, and if you want to use the same AC voltage controller for high power applications, we need to go for 3-phase AC voltage controller where we'll use the individual thyristors in back-to-back connections, because individual thyristors will have the high power capability. Here triac is having some limitations in the power capability. That's why we'll go for 6 thyristors. Okay, if we see the speed torque characteristics, so on the y-axis speed, on the x-axis torque, if we take the normal induction motor with some supply voltage V1, the characteristics looks like this, right? Normal induction motor. So this is nothing but starting torque TST1. So up to here, this is TST1, and corresponding maximum torque is here Tmax. Sorry, here the corresponding maximum torque is this one, and here this is synchronous speed omega ms, and slip s is equal to 1 or speed omega is equal to 0 to omega ms, where omega ms there the slip is equal to 0. So in this way the speed torque normal single speed torque characteristics looks like this. So if you are controlling the voltage, then what will happen to the speed torque characteristics, that we'll see. When you are decreasing the voltage, see here V1 is greater than V2 is greater than V3. So when you are decreasing the voltage, as your voltage starting torque is directly proportional to the E, which is directly proportional to V. That's why when you are decreasing the voltage, your starting torque also decrease, and whereas maximum torque, if you take, maximum torque is directly proportional to the E, which is directly proportional to V. When you are decreasing the maximum torque, when you are decreasing the supply voltage, your maximum torque also will decrease. Your starting torque is decreasing as well as maximum torque also decreasing when you are decreasing the voltage. And what about the slip range? SM. SM is directly proportional to R. SM is equal to R2 by X2, right? R2 by X2. So SM is independent on the variation in the supply voltage. That's why your maximum torque is at same slip range. Maximum torque is at same slip range. Without changing the maximum torque slip range, this is corresponding speed, or with respect to the maximum torque, the corresponding slip range. So that is not changing, only starting torque is decreasing. Here another, the supply voltage when you are decreasing to V2, the corresponding characteristics is shifted downward with reduced maximum torque and reduced starting torque. Further it reduces to reduced maximum torque and reduced starting torque. So here when we are reducing the voltage, how can we reduce the voltage? By adjusting the firing angle of the triac, we can control the output voltage of the AC voltage controller, where we have given that output of the AC voltage controller to the induction motor. That's why your input to the induction motor, whereas supply voltage to the induction motor is controlled by using the triac firing angle. Okay, so for first set of voltage, these are the characteristics where you are having the more starting torque and more maximum torque. As your voltage is decreasing, your characteristics are shifting downward. Without changing the slip range, your maximum torque and starting torque both are decreasing. So that controls the speed of the induction motor. In this way we can control the speed of the induction motor. Let us take one of the torque, let us assume that your TL load torque is directly proportional to the omega m square, or TL is equal K into omega m square. So that characteristics looks like this. So TL is equal K into omega square characteristics. These are touching the speed torque characteristics at these respective points. For V1 supply voltage, so this is the speed. The corresponding speed is omega m1. The intersecting point of the load torque as well as the motor torque are these torque points. So when we are reducing the supply voltage, the another intersect is with respect to the V2 supply voltage. The characteristics are intersecting at this point. The corresponding to the reduced speed torque characteristics, the speed is reduced to the omega m2, omega m3. Likewise, speed is reducing. So in this way, we can control the speed of the fan or speed of the induction motors. So generally, if we see the voltage also, how we are controlling the voltage means, if we take the single phase supply, Vs is single phase supply, VAB with solid line, and the opposite to the R during the negative half cycle, the minus VAB, right? Minus VAB, instead of minus VAB, I have considered here VBA. VBA is nothing but minus VAB. So with the dotted line, I have shown here the VBA. So the firing angle is provided at alpha and pi plus alpha. When we are providing the firing angle at alpha, from there onwards your thyristor will turn on. When the corresponding thyristor is turned on, it will follow similar to the supply voltage. It will follow similar to the supply voltage. If it is RL load, induction motor is inductive nature, right? Inductive type, that's why it will extend its conduction into the negative region also because of the current. Because current, if we take the I0 current is extended up to this beta point. Because of that beta, till the beta point the current is extended, your source voltage, your output voltage also extended till that beta point. Then again at pi plus alpha, the negative side thyristor is receiving the pulse, so that makes the thyristor into the forward bias, and during the negative half cycle also, in the negative side only you will get the voltage, because negative side thyristor is turning on when your supply is getting reverse. When your supply is getting reverse at pi plus alpha, the other thyristor as triac will work for forward bias as well as reverse bias equally. So from here onwards again current will charge and discharge, so that's why your voltage will extend into the positive region also till that pi plus beta, till this pi plus beta point, and the cycle repeats. So in this way, if you see here, if you are increasing the firing angle, instead of alpha here, if you are keeping alpha at here, your voltage will be from here onwards. In this way, the voltage will be controlled. By controlling the firing angle, your voltage will be controlled. That voltage control will reduce or increase the voltage. That increase or reducing the voltage will change the speed torque characteristics. The change in speed torque characteristics will intersect at different points of the load torque. That reduces the or increases the speed of the induction motor. In this way, the intersecting point will change as per the speed torque characteristics of the induction motor for various voltages. So that reduces the voltage, that reduces the or increases the speed of the induction motor. In a similar way, three-phase AC voltage controller means three-phase AC voltage controller also. So here we will use the back-to-back thyristors for three-phase supply RYB. So T1, T3, T5, which are connected anode to the supply, T1, T3, T5. This is the numbering sequence for the thyristors. Then T4, T6, T2, like in the rectifier, will give the upper switches T1, T3, T5, down switches T4, T6, T2. Those are connected to the induction motor. Through the shaft, it is connected to the fan or pump type load. And here in a similar way to the rectifier, will give the triggering sequence. At a time, two thyristors need to turn on to complete the circuit. So to at a time two thyristors means each thyristor, the angle difference from each pulse, one pulse to other pulse is 60 degrees, and each thyristor pulse need to continue its conduction till 120 degrees. So this, for example, if we provide the T1 firing pulse at 60 degrees, the next firing pulse will be provided in combination with the T2 switch at after 60 degrees. So for example, this is a pulse sequence. T1, T2, T3, T4, T5, T6 are turned on in this way. So in combination with the T1, T6 or after 60 degrees, again one more firing pulse to the T1 will be given, because T1 need to conduct for 60 degrees. The next T2, T3, T4, T4, T5, T5, T6 in combination, again here T. So at a time two switches, T1, T6, T2, T1, T3, T2, T4, T3, T5, T4, T6, T5. So earlier in the rectifier I have shown you with conduction period, but here simply with pulses I am showing here. So T1 pulse, in this way we need to provide the firing pulse. So we need to shift this firing pulses 60 degrees to get the T2 pulses. At 60 degrees difference we need to give two pulses. So T3 pulses, T4 pulses after 60 degrees. From here onwards, after 60 degrees T4. From here onwards, after 60 degrees T5, again two pulses, T6. As it is out of loop, another pulse will come in series in line with the T1. In this way we will provide the firing pulses to the three-phase AC voltage controller to get the controlled AC voltage, the output of the AC voltage controller. That will control the speed of the induction motor in this way, as shown in the speed torque characteristics. So this is all about the AC voltage controller. So next we will see the efficiency of the induction motor under voltage control. So how to calculate that efficiency of the induction motor under voltage control means, so let us assume here I have considered only rotor side equivalent circuit. This is your reactance X2 dash and R2 dash by S is the resistance, because slip will come as this is mechanical component. So your total input power is Pin, and by neglecting the stator impedance or neglecting the stator losses, your Pin is equal to Pg, where Pg is nothing but air gap power or rotor input power. So the output of the rotor is nothing but mechanical output power. So here Pin, stator input power, which is equal to rotor input power, by neglecting the stator impedance, Pin is equal to Pg is equal to 3 into, as this is 3 phase, 3 into I2 dash square into R2 dash by S. That is the total rotor input power, because we are having only resistance component here. 3 into I2 dash square into R2 dash by S is nothing but rotor input power or air gap power. So here we have again rotor copper losses. The rotor copper losses is nothing but only resistance we need to consider without slip component. So 3 into I2 dash square into R2 dash is nothing but rotor copper losses, because we can split this resistance into two components like this. So where we can keep R2 dash at one place and R2 dash into 1 minus S by S. This is nothing but fictitious resistance. R2 dash plus R2 dash by S minus R2 dash into S by S. That is nothing but minus R2 dash. Minus R2 dash and plus R2 dash will get cancelled, and we can get only R2 dash by S. But to find out the rotor copper losses, we split this R2 dash by S resistance into two components. So by using this R2 dash resistance, we can get the copper losses as 3 into I2 dash square into R2 dash. So now if you want to find out the mechanical power output, the air gap power minus corresponding rotor copper loss will give the remaining power. The remaining power is nothing but mechanical power output. P out is nothing but mechanical power output, which is nothing but air gap power or rotor input power minus rotor copper losses. So that will give the 3 into I2 dash square into R2 dash by S minus 3 into I2 dash square into R2 dash. That will give 3 into I2 dash square into R2 dash into 1 minus S by S. So that is your mechanical power output. To find out the efficiency is nothing but output by input. Here instead of taking the total input, we are considering the rotor input, where rotor input and total input are same by neglecting the stator impedance. That's why P out by P in is equal to mechanical output already we calculated 3 into I2 dash square into R2 dash into 1 minus S by S is divided by P in is nothing but rotor input power. P in is equal, rotor input power is equal 3 into I2 dash square into R2 dash by S. By doing that, your 1 minus S term will be the remaining term. Neta is equal, efficiency is equal 1 minus S, where S is equal to Ns minus N by Ns. Efficiency is equal N by Ns. So here if you see, efficiency will decrease with decrease in speed. As your speed is near to the synchronous speed, your efficiency will be 100%. We should run the motor near to the synchronous speed, then only we can get the maximum efficiency. If you are reducing the speed, your efficiency will come down or efficiency will decrease. So always we'll try to run the motor near to the synchronous speed, then it will maintain the good efficiency. Okay, this is all about the efficiency calculations of the induction motor. Thank you all.